In this video, we're going to continue our discussion of implementing hierarchical linear modeling in SPSS. And we're going to kind of break away from the standard and start exploring a little bit more, playing around with some interpretations, adding in some level 2 predictors, and generally doing some crazy stuff just to play around with this data a little bit more. So I'm going to go to where I was before, analyzed mixed models and linear, and I'm still going to have all the things as before, but I'm going to reset just so that we can re-explore this and remember how to do these, just in case we need a little bit more practice. So I'm going to include ID in subjects. I'm going to include math achievement as my dependent variable. I had socioeconomic status as a covariate. And now, you know what? I want to include female as an additional covariate. And I tell you what, let's go on and add in, I don't know, the whether or not this is a level 2 predictor, whether or not the school is a private academy. Let's go on and add that into this So I'm going to include all of these terms as variables in the model: socioeconomic status, female, which are both level 1 predictors. And so these are like X values, different, X sub 1 and X sub 2. And whether it's a private academy or not, this is a level 2 variable, so this would be a W. I'm going to make sure I include the intercept. In the random, I'm going to click include intercept. Again, you may already have this. I'm going to make sure IDs and combinations. And I'm not going to include any random intercepts for any of these at the moment. I might add that later on. There is no random intercept for private academy, because in this particular case, private academy is a level 2 variable. So the only random intercepts we could add, or random, slopes we could add, are for SES and female. For estimation, stick with restricted maximum likelihood. For statistics, again, parameter estimates for fixed effects and test for covariance parameters. I'm actually just going to use these two. Covariances of random effects is interesting, but it's kind of included in there, so I'm not going to worry about including that. I'll just keep using these two. All right, clicking OK. I now see I have my random components. That is, I have my schools that vary on the average math achievement, so they still statistically significantly vary. Socioeconomic status is still a statistically significant predictor, but now I can see socioeconomic status is a statistically significant predictor after accounting for female and the private academy. I could say after accounting for that, but again, I was already accounting for that in my earlier models by accounting for the school. So I can say after accounting for private academy, but that doesn't actually impact much of my socioeconomic status here. Though looking at this, private academy does impact math achievement. So this level 2 variable at the school does have a statistically significant effect on math achievement. You can see the degrees of freedom for the private academy are much different than my other degrees of freedom. Why this is because I have less schools than I have students. And so my degrees of freedom are based on the units that I'm using to assess this. So that's something to pay attention to. There is a manipulation. So if I added a random effect to SES, the degrees of freedom would drop to be in the level 2 degrees of freedom, because I'm allowing them to randomly vary. But here, when I don't have a random slope component, I can see the degrees of freedom are of the magnitude of my level 1 sample size for the level 1 variables, and for the level 2 variables, they're of the magnitude of my level 2 sample size. Note, none of these are identical to the level 1 or level 2 sample sizes because they're all interrelated. In this particular case, female has a very low effect, negative effect, but it's statistically significant. That is, girls are doing statistically significantly worse in math achievement than boys are. And so this data is, I believe, from 1988, if I remember right. And this effect is absolutely an effect, and we can see how much worse are they doing. Well, on average, they're doing about a point worse. So it's about half of a standard deviation in socioeconomic status. on average for females do worse in math achievement after accounting for socioeconomic status and whether or not they went to a private academy. All right. Well, that was interesting. Let's explore this female a little bit more. I've got two girls that are going to school. So let's see if we can figure out what's going on with females so that we can um, figure out how we can maximize the scores. Well, we looked at private academy, but maybe, this is the overall effect of private academy and this is the overall effect of female. Maybe what we need is an interaction between female and private academy. So what I can do is I can go to fixed and I can add an interaction term by clicking on female and then holding the control button and clicking on private academy. So I have them both selected and then clicking add, and that adds an interaction term between female and private academy. And if you think about this, again, private academy is a level 2 term, female is a level 1 term. This is a level 2 and level 1 interaction. Clicking OK to run this model, now I can see it doesn't really matter if the girls went to a private academy or not. There is no interaction. That is, private academy has its effect, female has its effect, and the fact that girls went to a private academy doesn't really change much of anything. All right, well, that didn't change much, so maybe I'll go into my model. I'll take out this interaction. I won't worry about that. But maybe schools are different for girls. So like maybe some schools have a better effect on girls than boys. Maybe the impact of female and math achievement, again, schools have an impact here. So I'm going to add female to the model in my random components so that each school can have its own impact on girls and their relationship to math achievement. I'm going to remember to change my covariance type to unstructured now that I'm adding a random slope component, and click OK, and then run this analysis. Scroll on down to look if the schools statistically significantly change. Well, my female prediction component didn't, but looking down here, well, no, I don't really see a statistically significant impact of schools on females. So that is to say that schools don't really seem to be affecting the relationship between how well girls are doing on math achievement. All schools seem to have the same problem here. All right, well, let's keep playing around here. All schools seem to have the same problem. I'm going to remove female from the random effects. I've got private academy. What else can we add here? Let's how about school size? Let's add that in. And I tell you what, let's look at the interaction. Let's look at female and size. Maybe school size is going to have an impact, and maybe girls do better at smaller size schools, or girls do better at larger size schools, or something like that. Let's kind of explore that out. So I'm going to click OK. Oh, and I'm getting a warning. So I took out my second random effect. And so it's giving me a warning that I used an unstructured covariance structure with only a single intercept random effect, which I shouldn't do. So that's a problem. I apologize for not catching that in Analyze Mixed Models Linear in the random place. Once I took out this random effect, I should have changed unstructured back to variance components. And then it's not going to give me that big nasty warning message. All right, so let's look through here. Blah, 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 blah. Oh, this is interesting. Okay, here we go. So socioeconomic status, still a statistically significant impact on math achievement. But now female doesn't have a statistically significant impact on math achievement. So including size in this interaction, oh man, now we figured out the trick. It's that we have to include the school size, and now we can see females don't have, or whether you're a girl or a boy isn't statistically significantly impacting your math achievement score. And we can say things like, yay, that's fantastic. And we have the size as a statistically significant impact, and the female times size, that is the interaction term, is statistically significant, which means we do want to have caution when interpreting female and size because they depend on each other. And I don't know if any of you have caught this, but my interpretation of female and that main effect is premature. And what I mean by this is, remember our rule with interactions. And that's not because this interaction is statistically significant, but when I include the interaction term, the interpretation of the main effect term is interpreted when the other variable is at 0. So what this is telling me is that female are not statistically significantly different in their math achievement scores than males at schools of size equal to 0. And a school of size equal to 0 doesn't really make practical sense. So this interpretation and this lack of statistical significance is actually nonsensical. And so we have to be really careful about that. In fact, we probably can't interpret this as it is. We're going to have to go make a change because of this interaction effect. Now, size interpreted when female equals 0. Well, when female equals 0, we're talking about males. So this one actually can be interpreted. We just say there's a statistically significant relationship between the size of the school and math achievement for female equals 0, which is males. So that's what we're saying here, is that there's a significant relationship between size of the school and math achievement for males. And we can interpret that. In fact, calculating like a mean-centered female doesn't actually make much sense when interpreting the effect of size. But female equals 0, again, is sensical, and so interpreting size is okay. But size equals 0 is nonsensical, so interpreting female here is not okay. And again, it's weird that when I'm interpreting female, it's the other variable in the interaction, size, that's 0. So when I interpret one, we interpret the one when the other one is 0. So interpret female when size is 0, interpret size when female is 0. And it's because we're allowing the interaction between those two. All right, so again, this female, it looks good, but it looks good because it's a pretend number. It's for when school size is 0. Instead, let's talk about school size being the average size. So I need to make a new variable for size. I need to make a centered size that's centered around its average. And for that, I need to find the average size. So I'm going to go up to Analyze, go to Descriptive Statistics and Descriptives, and I'm going to move size into the variable and hit OK to find the mean size. The mean size is 1056.86. And now I'm going to create a centered variable using transform compute that I'll call C size for centered size. Move size over here and subtract its mean that I just calculated. The mean of size is 1056.86. So this is going to center that variable size. And now when I include the centered size in the analysis, when I'm interpreting female when size equals 0, size equals 0 will now represent the average school size. So this is my centered school size. I'm going to go up to Analyze, Mixed Model, Linear. Maintain that subjects are going to be listed within school ID. That doesn't change. But now I'm going to go take out regular size and include centered size. Now it's important to realize I just removed regular size in all of my things. So if I had a random component associated with that, that just got removed. If I had fixed components associated with that, that just got removed. If I had interactions associated with that, those got removed. So I have to go add everything in related to centered size. In this case, I'm going to have to add in centered size and then select centered size and female to look at the interaction. And I have to add both of those in. And don't forget to add in both the main effect and the interaction effect. I didn't have any random effects associated with centered size, so I'm not going to include that here. I'll simply click continue. And I'm not going to change any of my other options, so I'll click OK. So this is going to run the analysis, the exact same analysis as I had, but it's going to run it with a centered size. That is size minus its mean. And the reason we did that is because female as a coefficient was interpreted when size was 0, which on its original scale, a size of a school with 0 students was uninterpretable. But on the centered scale, a size of a school with 0 represents the average school size, and that has a much better interpretation. All right, well, let's scroll down and look at this interaction effect. Again, all the rest of these, what I'm really focused on is female, because that's the one I was concerned about. You'll see centered size has the exact same effect as earlier. The interaction has the exact same effect as earlier. The only thing that's changed is the intercept and the interpretation of female. And the interpretation of female, now I can see far from females not having a worse average math score after I've accounted for the interaction. Once I account for the fact that, yeah, we're not looking at schools of size 0, we're looking at schools of average size. When I interpret female now, I can see female is still interpreted as having a worse overall math achievement score than males when I'm looking at the average size school. My takeaway from this is, again, females are typically doing worse in math achievement, even after accounting for school size and accounting for the interaction between school size. But what I learned from that first analysis was that at smaller levels, females tend to do better. So for smaller schools, girls are actually doing better. That is, they're doing more comparably to boys in smaller sized schools. That's kind of an interesting finding. Again, the first analysis had the small size, quote unquote, listed at school size equals 0, which was far, far too small. But this might be worth creating an interaction plot to explore, or recentering to explore, well, what if the school was size 100? What if the school was size 200? And explore what those female statistical significance values are to see, hey, at what point are girls struggling more than boys in math achievement statistically significantly. All right, well, this has been an exploration of a couple of different models, playing around, fitting, looking at different questions, looking at different interpretations, kind of exploring based on if questions change, how I can do that, and ultimately ending in a big warning. The misinterpretation of the female with not centering my independent variables, and then centering the independent variables so that I can have the correct interpretation of female. Again, for an average school size, girls are struggling more than boys in math achievement statistically significantly, as opposed to that initial interpretation, if I wasn't careful, which is after accounting for school size, girls aren't struggling anymore, and that would be an untrue interpretation, because that is an interpretation for schools of size 0, which is a non-existent group.